Welcome back, my fellow programmers. Hopefully, we all made it through 3.5 unscathed. Let's wrap it up with 3.6 equivalent Boolean expressions. Our first topic, negating relational operators. Our learning objective, we want to compare and contrast equivalent Boolean expressions. It's time for backward talk with Bizarro. For those of you not familiar with Bizarro, he was a clone of Superman that came out a little different. When Bizarro speaks, he means the opposite of what he says. So, what do you think Bizarro means when he says, "Me am not Bizarro"? Ding ding, the correct answer is, "I am Bizarro." You just need to logically negate what he originally said. What does Bizarro mean when he says, "Bizarro, am sad to meet you"? He is trying to say, "I am happy to meet you." Let's try another one. Bizarro says, "We am not going to have a slightly bad time." What did Bizarro mean? We are going to have a very good time. I think so too, Bizarro. Now, before we can negate relational operators, let's do a quick review and take a look at what our 6 relational operators are. 4 of those relational operators have a precedence level of 9. They are our less than symbol, our less than or equal to, greater than, and greater than or equal to. Our remaining 2 relational operators have a slightly lower precedence level of 8. That is our equal to operator, where we use 2 equal signs in a row, and our not equal to operator, where we use our not operator followed by the equal sign. Taking a look at some Boolean expressions in the top row of the table, we have num greater than 8. What would be some values of num such that that Boolean expression would evaluate to true? Some example values would be 12, 124, and 882. If we plugged any of those in for num, that Boolean expression would evaluate to true. Our range of values is 9 through positive infinity. What if instead we wanted numbers that were less than or equal to 8? What would be some sample values that would make that Boolean expression evaluate to true? We could use -12, we could use 0, we can even use 8. If we plug in 8 for num, that Boolean expression would still evaluate to true. Therefore, our range of values is negative infinity to positive 8. One last Boolean expression to look at. We have not, and then our parentheses, num greater than 8. What values can we plug in for num to have that Boolean expression evaluate to true? Well, we could use -12, 0, or 8. If we plugged in -12 for num, we are asking if -12 is greater than 8. That would be false, and then not false is true. So we are looking for numbers that are not greater than 8. Therefore, our range of values is negative infinity to positive 8. When we say num less than or equal to 8 and not numbers that are greater than 8, those are equivalent expressions. Taking a look at just a portion of a number line, when we say we want numbers that are less than or equal to 8, that means we want numbers in this range. If we say we don't want numbers that are greater than 8, we are saying we don't want these numbers, which then just leaves us the numbers 1 through 8 on this number line. Those are the numbers that are not greater than 8. We can use a not operator to write equivalent expressions. So when we start off with a Boolean expression and we have the not operator outside of our Boolean expression, if we want to write an equivalent expression, we distribute that not operator into the parentheses, it will meet that relational operator and it will then negate that relational operator. So our original operator was greater than or equal to. The opposite of greater than or equal to would be less than. So the first statement is saying we don't want numbers that are greater than or equal to 10. Another way to say that is we just want numbers that are less than 10. Another example, we have not numbers equal to 10. We distribute in the not operator. We negate the relational operator. The opposite of equal to is not equal to. In the first statement, we are saying that we don't want numbers that are equal to 10. In the second statement, which is an equivalent expression, we are saying we don't want numbers that are equal to 10. In the tables on the bottom, we see how to negate each of our 6 relational operators. So when we say we don't want numbers that are greater than or equal to x, that means we want numbers that are less than x. Negating the greater than or equal to gives us the less than. When we say we don't want numbers that are greater than x, that means we want numbers that are less than or equal to x. And then you can look at the examples for the other 4 relational operators. Sometimes we will start off with a Boolean expression that does not have a not operator in it. And if we want to write an equivalent Boolean expression, in this case, we factor out a not operator. That not operator will go outside of our resulting Boolean expression. We still need to negate the relational operator. When we negate a less than, we get a greater than or equal to. So originally we are saying we want answers that are less than 10. That is the same thing as saying as we don't want answers that are greater than or equal to 10. Looking at the second example, we are saying that we want answers that are not equal to 10. We want to factor out our not operator. That not operator goes in the front of our resulting Boolean expression. We still negate the relational operator. The opposite of not equal to is equal to. And so the equivalent Boolean expression is that we don't want answers that are equal to 10. In this table, we see 6 Boolean expressions. Take a minute and try writing the equivalent Boolean expression in the space on the right. Our first Boolean expression is we don't want numbers that are greater than 8. The equivalent Boolean expression, we want numbers that are less than or equal to 8. In our second example, we don't want answers that are greater than or equal to 15. The equivalent Boolean expression, we want answers that are less than 15. Our third example, we do not want I values that are equal to 3.2. The equivalent Boolean expression, we want I values that are not equal to 3.2. Fourth Boolean expression, we want values that are less than 2. That means we don't want values that are greater than or equal to 2. The fifth Boolean expression, we want results that are not equal to negative 12, which means we don't want results that are equal to negative 12. And our final Boolean expression, we want x values that are less than or equal to 22, which means we do not want x values that are greater than 22. This aligns with our essential knowledge. Equivalent Boolean expressions will evaluate to the same value in all cases. Our next topic is De Morgan's Law, our learning objective. We're going to compare and contrast equivalent Boolean expressions. You all remember De Morgan, right? Who could forget when he said the complement of the union of two sets is the same as the intersection of their complements, and the complement of the intersection of two sets is the same as the union of their complements? I'm sure it changed your life. When I heard it, I said, huh? What, De Morgan? They tried to clear it up by saying, The negation of a disjunction is the conjunction of the negations, and the negation of a conjunction is the disjunction of the negations. To which I said, uh, oh, uh-huh. To which then he tried to clarify by saying, not A or B is equal to not A and not B, and not A and B is equal to not A or not B. Now that we have that law, we get to apply that law. We're going to see how that law applies by meeting some very specific people. First, we have a Boolean expression that says is jolly and is green. If you were to imagine someone that would make that Boolean expression evaluate to true, you might think of the jolly green giant. Both of those adjectives are directly in his name. He is jolly and he is green. We're going to look at some of the equivalent expressions from De Morgan's law. De Morgan said, not is jolly and is green is equivalent to not is jolly or not is green. When you hear the first one, not, and then the parentheses is jolly and is green, you might think that you can't be jolly and you also cannot be green. That is not the case. That is not what this statement is saying. The statement is saying that you are either not jolly or you are not green. Yes, you could still also be not jolly and not green, but you only just need to be not one of these two things. If we were to imagine some characters to make these equivalent Boolean expressions to evaluate to true, you might think of Jollibee, or you can also think of the Incredible Hulk. Looking at Jollibee, Jollibee is jolly. However, Jollibee is not green. So you can be one of these two things, or you could be neither of these two things. The only thing that we are saying is that you are not both of these things. We are just saying you are not jolly and green. You could be jolly or you could be green. So the equivalent Boolean expression is you are either not jolly, which is the Hulk, or you are not green, which is Jollibee. Looking at our last two equivalent expressions, we have not parentheses jolly or green. That is the same thing as saying that you are not jolly and you are also not green. If we were to think of someone to make these Boolean expressions evaluate out to true, we could imagine the Red Hulk. The Red Hulk is not jolly and the Red Hulk is also not green. How we move from one of those expressions to the other equivalent expression is if we have the not operator on the outside, the not operator gets distributed in and negates each part. So not is jolly is not is jolly. Not and is or, and not is green is not is green. And that is how we create those two equivalent expressions. Looking at our next set of expressions, if the not operator is in the inside, we can factor out the not operator from each part in there, logically negating everything in there. Inside we have not is jolly. If we factor out the not to negate that, that is just jolly. We have our logical and. If we factor out the not, we negate that to an or. And if we have not is green, factoring out the not logically negates that to is green. So we have the not operator on the outside, and inside the parentheses, we have is jolly or green. And that's how we get those two equivalent Boolean expressions. It really is just a series of steps that you need to follow. When we have the not operator on the outside of our parentheses, we want to distribute in that not operator by following the steps. The first step is that we want to identify all relational operators. Our first relational operator is the greater than sign. Our next relational operator is the equal to sign. Then we want to identify all logical operators. We have one logical operator in there, which is our logical AND. We don't do anything with arithmetic operators. We leave that mod operator alone. Step 3, we logically negate all identified operators. Greater than becomes less than or equal to, and becomes or, and equal to becomes not equal to. And then we remove the not operator from the outside because we distributed it in. This aligns with our essential knowledge. De Morgan's law can be applied to Boolean expressions. Equivalent Boolean expressions will evaluate to the same value in all cases. Here is our next example. The first thing that we need to do is identify all relational operators. Our first relational operator is here with is fine. Remember, when we just say is fine in a Boolean expression, that is hiding the relational operator of equal to. We are really saying is fine equal to true. Our next relational operator is over here with is dandy. And then we need to identify our logical operators. We have the logical operator of and in the middle. We distribute in the not operator to logically negate all identified operators. Is fine becomes not is fine. The and becomes or, and is dandy becomes not is dandy. And we do not write the not operator on the outside. Looking at one more, we're going to identify our relational operators. We have our less than or equal to 0, and we have our not has lives. And then we need to identify our logical operator, which is the or in the middle. We logically negate them. Health less than or equal to 0 becomes health greater than 0. The or becomes and the not has lives just becomes has lives, and we remove the not operator from the outside. Starting off with an expression that does not have a not operator on the outside, to write an equivalent Boolean expression, we are going to factor out a not to put on the outside. We are going to follow some very similar rules that we did when we distributed in the not operator. We still start off by identifying all of our relational operators. In this case, we have our greater than sign and our not equal to sign. We still identify our logical operators. We have the and operator, and we still logically negate all of those operators. Greater than becomes less than or equal to, and becomes or, not equal to becomes equal to. The one step that differs is now we write that not operator outside of the parentheses. And now we have just created two equivalent Boolean expressions. Our next example is down and is out. Identifying relational operators, we have is down and is out. Identifying logical operators, we have and. Logically negating those, is down becomes not is down, and becomes or, is out becomes not is out. Last step, put the not operator outside the parentheses. Our final example of applying De Morgan's law, identify your relational operators. We have our equal to operator, and then we have not is playing. Identifying logical operators, we have the or. Logically negating those operators, equal to becomes not equal to, or becomes and, not is playing becomes is playing, and we write our not operator on the outside. Our final topic for Unit 3 is truth tables. Our learning objective, compare and contrast equivalent Boolean expressions. I always get a little sad when we get to the final topic in a unit. Now, am I telling the truth, or am I just doing some bizarro talk? You'll have to decide. So our final topic focuses on truth tables. A truth table will present us with some Boolean expressions. In this case, we have the Boolean expression A and B, and we also have the Boolean expression A or B. And we want to find out all of the possible outcomes of working with this Boolean expression. There are 4 possible outcomes. The first one is when A is true and when B is true. A second outcome would be when A is true and B is false. A third outcome would be when A is false and B is true. And the final outcome would be when A is false and B is false. There's no other way that we can arrange those true-false values to get a different outcome. So when A is true and B is true, A and B evaluates to true. When A is true and B is false, A and B evaluates out to false. When A is false and B is true, A and B evaluates out again to false. And when A is false and B is false, A and B once again evaluates out to false. So those are our 4 situations that we can have when working with this Boolean expression, and those are the 4 results that we could get. Our next column, we have A or B. Work down that column and determine the 4 possible outcomes we can get when working with that Boolean expression. When A is true and B is true, A or B evaluates out to true. When A is true and B is false, A or B evaluates out again to true. When A is false and B is true, A or B still evaluates out to true. And when A is false and B is false, A or B will then evaluate out to false. Now you might see all sorts of different types of Boolean expressions in your truth table. Here you are presented with a Boolean expression. Work down that column and see what all 4 possible outcomes would be. Now looking at that Boolean expression, we have not, and then we have parentheses, not A or not B. Even I think that is too complicated of a Boolean expression. By seeing the not on the outside of the parentheses, that reminds me that I can apply De Morgan's law to this Boolean expression and maybe come up with a different, simpler Boolean expression. So let's apply some De Morgan's law by distributing in that not operator. When that not operator goes in and meets not A, that just becomes A. When that not operator distributes in and meets the or, that becomes an and when the not operator distributes in and meets not B, that turns into B. These are equivalent Boolean expressions. One of them looks way nicer than the other one. So by applying just a little bit of De Morgan's law, it can help you complete these truth tables because this column is really easy to complete. In fact, we already completed it. We know that the only way this evaluates to true is when both A and B are true. Otherwise, it evaluates out to false. Since these are equivalent Boolean expressions, the answers that I got in this column will be the same answers that I would get for this column. And so now I filled out this column of the truth table without having to evaluate this statement at all. This aligns with our essential knowledge. Truth tables can be used to prove Boolean identities. Not only does this bring us to the end of our lesson, it brings us to the end of our unit. Make sure to rate how you are feeling about those learning objectives. Read over your recap statements. Hit me up with any questions or concerns that you have regarding these concepts. Join us in our next video, which will be for our next unit, and keep programming.